today about the weird and wonderful things that NASA's Cassini spacecraft has been sending back about Saturn. I'm your moderator, Jari Cook. I'm the Cassini media rep based here at NASA's Jet Propulsion Laboratory in Pasadena, California. JPL is where Cassini's mission is managed, but we have some great speakers for you today from across the country. So our hangout today is provocatively titled Weird and Wonderful Saturn, but we'll have some scientists here to tell you why some of the things that might seem weird on the surface aren't actually all that weird. So our hangout is going to happen in 3 acts. Our first act is going to be brought to you by Kunio Sayanagi. He's a Cassini Imaging Team Associate based at Hampton University in Virginia. He's going to be telling you about this really unique 6-sided jet stream around the North Pole of Saturn that we call the hexagon. We've actually just released some new images and video of the hexagon, which you can see on our websites at nasa.gov/Cassini and saturn.jpl.nasa.gov. He's going to be showing you our new views of the hexagon and telling you a little bit about, how it works. Our second act is going to be Carolyn Porco. She's our imaging team lead. She's based at the Space Science Institute in Colorado. She's going to be talking about this really gorgeous multi-image mosaic that Cassini has been able to put together of the Saturn system. It shows Saturn, its rings, a lot of moons, and then also our inner planets of our solar system. She's going to give you a tour through the image and then tell you how it came to be. Our third act is going to involve Linda Spilker and Earl Maize. Linda is our Cassini project scientist, and Earl is our Cassini program manager, and they are based here at JPL as well. Linda is going to tell you what's coming up next for Cassini science, all the exciting things that we're going to do in the next couple of years, and then Earl is going to tell you how does our spacecraft do all the acrobatics it needs to do in order to get that great science. So we're going to start off with Kunio.
Hi. So I will be talking about the images we are releasing today of Saturn's hexagon, and that. So we are looking at Saturn from Cassini spacecraft's vantage point, which is in orbit around Saturn since 2004. So I have been studying this feature called the hexagon around North Pole of Saturn. The feature is not new. Just to be sure, we've known that it existed since at least since '81, and we confirmed that as soon as Cassini went into orbit around Saturn, it was still active in 2004. I think we're still waiting for the image. So we are in orbit around Saturn. The images we're releasing today, let's see, the image that just showed up is how Saturn's north polar area looks like from orbit of Saturn. So right in the middle is North Pole of Saturn, the darker spot, and then you can see the clear geometric hexagon, geometric shape, which has 6 sides and corners. That's why we've been calling it the hexagon. So this is the view we have from the orbit. And let's see. So what's new about what we are going to talk about today is the view we have. Saturn's North Pole was in winter darkness when we entered orbit around Saturn in 2004, and sunlight has been slowly starting to shine on North Pole during the earlier part of the mission. And then that brings us to the next image that we released in 2009. So this is the view we had in 2008 and released in 2009. So we still had a hole around North Pole. This is the best image we had previous to today, before today. So you can still see the hexagonal pattern. You can see the wavy patterns radiating off of the corners. So this is what we started seeing around 2008. And then let's move on to the view we have today. Cassini has been in orbit around Saturn since 2004, and we change orbit once in a while so that we can have a better view of different parts of the planet. So Saturn went through an equinox earlier, a few years ago, and we just changed Cassini's orbit so that we can have better views of North Pole, so that we can have movies like this. So this is a view we had about a year ago. And then it takes us a bit of time to put together, make a map. We had to stitch together tens of images to put together this movie. And this is the view we have today. In the middle, you can see the counterclockwise spinning fast vortex. We have been calling it the polar hurricane. And then you see around the around 5 o'clock spot, you can see a counterclockwise, clockwise spinning vortex. That is another vortex. And then you see, of course, the hexagonal pattern and outline. So I hope you can see the clouds zipping through the hexagonal outline. This shows that the hexagon is actually a feature, geometric pattern formed by the jet stream at that latitude. So the jet stream has a lot of effect on the cloud dynamics, and we can, in another of the view we are releasing today, we can actually tell a little bit more about the cloud properties of the clouds affected by the jet stream, which is coming up now. So in this view, I hope you can see the sharp color boundary between blue to darker color and then green. That is the color boundary formed by the jet stream. So a jet stream can act as a transport barrier. Let's see, it can prevent materials from going across the jet stream because it's just blowing so fast. You can kind of imagine that it's easy to move along the stream of the jet, but it's really hard to cross that stream. So when there's a strong jet stream blowing like this, it tends to create a wall like this. And in this image, this is a false color view. Red color is responding to large particles, or large droplets of clouds, and then green channel is assigned to similar particles but at higher altitudes. So red is deep, big particles. Green is high, large particles. And then the blue channel is assigned to a wavelength that is responsive to tiny aerosols higher up in the atmosphere. So this color composite is showing properties of clouds that exist in different areas. And you can clearly see that there's a sharp boundary in the composition or makeup of the clouds that we see across the hexagon. So I've been talking about, I said that this jet stream has a six-sided pattern. It looks really, well, peculiar maybe. And it is, the surprising thing is that it's really stable. It has been there since at least 1981. This is a really exciting thing we can see. It looks, you might think that it's really weird, but a similar thing actually happens on Earth, which is the next movie that we're going to show. Earth has atmospheric jet streams. This is the weather system. This is the flow that moves the weather systems across the North America continent, for example. Across North America, you might notice that we see weather patterns moving from west to the east. So West Coast feels the weather, the storms before they reach East Coast. That is because there's this jet stream flowing across high altitudes around Earth. So that actually totally wraps around the planet. And you can see that this path of this jet stream is actually meandering. And but the meandering shape is not stable on Earth because on Earth, that jet stream has to blow over mountain ranges and it has to cross the boundary between the continents and oceans. Earth is basically really messy. So the interaction between the hard ground and the jet stream is going to make an unstable pattern. But of course, Saturn is a gas giant planet. That's why Saturn can maintain a kind of stable geometric shape. And then I talked a little bit about the compositional boundary that was created by the jet stream. Similar thing actually happens on Earth, which is called the Antarctic ozone hole, which we are going to show next. Here, the colors are showing that blue is region with less concentration of ozone, and then green and warmer colors are showing higher concentration of ozone. The outline of this ozone hole is actually maintained by another jet stream that's blowing around Antarctic continent. So this is another example of a wall that was imposed by a jet stream. Inside a jet stream, the ozone is destroyed, depleted by man-made CFCs. and the ozone that was created outside cannot go inside of the jet stream. That's why there's this hole of ozone that gets maintained during winter in Antarctica. So I like to compare the atmospheric dynamics, the weather systems of Saturn and Earth because, well, the goal here is to understand this thing called weather. So I like to talk about, when I talk about why study other planets, I like to say, well, bring up the topic of psychology. You do not claim to understand psychology by just talking about one person, not just by studying one person's mind. If you want to understand psychology, you study many, many persons. So it's the same thing about weather. When you want to understand weather, you don't just focus on one planet. Just in our solar system, we have a lot of atmospheres, starting with Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and then Saturn's moon Titan. They all have interesting weather systems, so it is really important to compare all these different weather systems, and so that we develop a wider range of perspective on our understanding. And that's all I have.
Okay, great, Kunio. Thanks very much. Just for all of you guys out there participating in our Hangout right now, just wanted to let you guys know how you can ask questions. You can ask questions on the Google Hangout page itself. You can ask them in the chat box on Ustream. You can also ask them on Twitter via #AskCassini. And you can also do it by email if you want it the slightly more old-fashioned way. Email vmcgregor@jpl.nasa.gov. So we'll be taking those throughout, and we're going to break up each speaker session with some questions at the end. So, well, for Kunio, let me just ask you my first question, which is, how excited were you to see these images? I mean, you know, the false color one, it's pretty psychedelic, and to see a complete view, I mean, how exciting was it to actually see these things come down?
I actually remember the evening I first processed those images. Those images came down, and then I got to see the images. So the first thing I do when I get these images is to generate maps. So I showed you the very first image that was in perspective view from Saturn. It's actually really hard to tell where exactly on the planet those cloud features are. So the first thing I do is to project it on a known coordinate system. And then when I do that, I can start tracking things, and then I can start stitching together the images. So when I first started getting the images that covered the hexagon, the images actually didn't show the entire hexagon, but as I started stitching together the images, the full view of the hexagon, actually in color as well, came into view. That evening, I was actually just going to process just the very first frame. I was pretty tired. I was about to be done with the first image about 1 a.m. I actually worked late at night. And then I was going to go home, but as soon as I saw the very first image, I just couldn't stop, right? I just processed the rest of it, and I just stayed up until 5 a.m. So yeah, that was a really memorable evening.
Well, great. So then one question that came in via email is, what's your favorite image of the mission? I mean, is it this hexagon one, or have you got some other ones that, you know, are dear to your heart as well?
Well, the hexagon is definitely very memorable. Let's see. Yeah, the 2008 view of the hexagon, that was really exciting because that was the very first complete view of the hexagon under sunlight, and then that was the highest resolution ever of the feature as well. Let's see. Something that comes close are the images of the storm. There was a storm that blew up in December 2010 and lasted for 200 days. It was a single thunderstorm, giant thunderstorm that kept going for 200 days, and we had a lot of good images from that. We got a lot of press coverages out of the images, and many of those, the turbulent wakes, showing a lot of details in the storm dynamics. Those images are very well. I don't think well, those are different features. I really like both the hexagon and the big storm. Yeah, those are the two big things that had happened during Cassini. So, yeah.
Okay, well, I know it's a little like choosing among your children, and you can't really have a favorite.
Exactly. Yeah,
but someone who's also really familiar with images, and in fact, the whole span of all the images that Cassini has been sending back for the over 9 years that we've been at Saturn is Carolyn Porco. So Carolyn, why don't you tell us a little bit about the big multi-image mosaic that Cassini took on July 19th of this year?
Okay, well, I have, I think, the best job of everybody here, because I get to tell you about this fabulous and unusual event that occurred on July 19th, an event we call the Day the Earth Smiled, on which we took the Cassini cameras and turned them in the direction of Saturn and the Earth and took a big glorious mosaic like I just told you. And my attachment to the idea of taking a picture of Earth goes all the way back to Voyager. When I worked with Carl Sagan on what has now become the very famous pale blue dot. That pale blue dot was actually part of a mosaic of 6 planets in the inner solar system. And I had this idea. I'd just been added to the Voyager imaging team, and I had this idea that it would be fabulous to show the world what our solar system looked like to the point of view of an alien making an approach from outside the solar system and approaching our star. And I had found, after I came up with this idea, that Carl Sagan had come up with this idea 2 years before I did, and in fact other people had also come up with this idea. So I joined forces with Carl, and he and others planned and executed the pale blue dot image. Now, if you recall, the pale blue dot image, and let's bring that up to show everybody, remind them what it looked like, the pale blue dot image was not a great image. You kind of look at it and say, what, you call that an image? It was just the dot of Earth, no stars. So I forgot to add, in Carl's proposal to the Voyager project, he said the idea was to take a picture of the Earth, and I quote, awash in a sea of stars. Well, you look at the pale blue dot image, and you don't see any stars, and you see the Earth sitting on a beam of light that is in fact scattered in the optics of the camera. Of course, none of this really mattered, because it was what Carl had to say about this image and the way he romanced it and turned it into an allegory of the human condition that ever since has made the phrase pale blue dot synonymous with an inspirational call to protect the environment and a call to planetary brotherhood. Well, ever since the beginning of my tenure as the leader of the imaging team on Cassini, I have wanted to do that picture over again, only make it better. And somewhere along the line, it occurred to me, wouldn't it be just absolutely fabulous if we could, at the moment that, if we could tell people in advance, at this moment, your picture is going to be taken from the orbit of Saturn, 1 billion miles away, and invite them at the appropriate time to go out, look up, and with an acute sense of awareness, contemplate their cosmic whereabouts, think about the utter isolation of the Earth in the never-ending blackness of space, marvel at the beauty and the rarity of our planet among all the planets around the sun, appreciate the lushness and the life on our planet, and marvel at their own existence, and also appreciate and contemplate the magnitude of the accomplishment, the technological and scientific accomplishment that made this interplanetary salute between robot and maker possible. And so that's in fact what happened. On July 19th of this past year, the Cassini cameras were turned towards Saturn while it eclipsed the sun, and it took another pale blue dot image of the Earth, and we sent out the word ahead of time: get out there, feel the cosmic love, smile in celebration, and to borrow a line from Bob Dylan, dance beneath the diamond sky with one hand waving free. And I have to say, we had a lot of help in spreading the word. An organization called Astronomers Without Borders spread the word. They organized events all over the globe. And JPL did its own Wave at Saturn program, which I'm sure you all know about and you're going to hear about afterwards. But the whole thing just went off tremendously well. It was joyous. People all over the world got involved, and they responded exactly the way I had hoped. We got a lot of comments. Some of the comments I got, of course, we got comments like, I hope you saw me. I'm the one wearing the funny hat. But by and large, we received many comments. I want to read some to you because they're wonderful. Someone, Richard from Pennsylvania, wrote, "What a great way to feel connected to the universe, the planet, and every single person on it. We are truly all in this together." And Tess from somewhere, I don't know where, said, "At the appropriate time, I left the table at a restaurant and I went to the parking lot. I turned my face to the sky and I spent a few minutes watching and listening to what life on Earth was like right there, right at that moment, knowing that millions of miles away, a spacecraft was turning its lens towards our amazing planet and taking photos. What a feeling of connection and oneness with the miracle that is life on Earth. This experience was beyond meaningful. It was transcendent. What a beautiful thing." And then finally, from Lake Ontario, "I had been entranced by this project ever since I heard about it and was determined to join in the celebration. I just never knew how emotional I would feel. I stood on the edge of Lake Ontario and I spun in circles waving at the sky. We may not be unique, we may be transient, we may be only flying along on a dust mote, but darn it, for 15 minutes we were there, we were aware, and we smiled." And so the whole thing was a great success. And here now is the image that was taken on the day the Earth smiled. And if you really want to see the details in this image, you won't see them in pictures we could show you on a Google Hangout. You'll have to go on the web. There are many places, as you probably know. They're on the Cyclops website, they're on the JPL website, they're on the NASA website, and in fact the image has gone viral. It's many places. But you can see center stage, you can see the globe of Saturn. It's eclipsing the sun, so the sun is behind it. The main rings, they look like they're glowing. The sunlight is actually diffusing through them. You see the narrow G ring, but the big blue ring that you see, the beautiful one, is most prominent, and that ring is created by 100 geysers erupting from the South Pole of Enceladus. I'll say more about that in a minute. And also in this picture, we captured 4 planets. We captured not only Saturn, Venus and Mars, and of course the Earth. So I think that this may be the only picture that's captured that many planets since the day of Pale Blue Dot, since the day of Voyager, which captured 6. And then the next picture is a close-up of Enceladus. I want to concentrate on Enceladus because I feel this is our most profound discovery with Cassini. You see the plume of material issuing forth from the southern half of the moon. That is, as I said, it's a material erupting from 100 geysers, and they come from what we believe is a habitable zone within this small moon. And because those geysers are connected to this reservoir of liquid water suffused with organic material inside this moon, it makes Enceladus the most accessible habitable zone in all the solar system. You can fly through those geysers and scoop up material, and it's not out of the question that it could be snowing microbes at the south pole of Enceladus. So this is just one of very many reasons why we really are desperate to make sure that we can continue through the rest of the Cassini mission out to 2017, because Enceladus is one of the prime targets that we wish to focus on. And then, of course, in this picture, you look over the right shoulder, as it were, of Saturn beneath the rings, and you will see our planet Earth right there, that bright dot. And again, you may not be able to see it on the screen, but if you go on the web, you will see that it is awash in a sea of stars, and it is there 1 billion miles away, and this image freezes in time, a unique moment when people all around the globe, at the instant this picture was taken, were saluting Cassini and thinking about the magnificence of what we have accomplished in exploring the solar system. And I have to add that I can't help but, when I look at this image, think that it represents the very, very best that humanity has to offer. Because we are, no doubt, the small and troubled and warlike inhabitants of one tiny little dot of a planet. But it serves us well to always remember we are also the seekers and the thinkers and the explorers who took this picture. One world, clear across interplanetary space to it. And to be that small and reach so far is, in the end, what makes us the extraordinary citizens of planet Earth. So if you're ever down and out and you're listening to the news and you hear nothing but one bad thing after another, go look at our Cassini picture of Earth and be reminded of just exactly how far we have come and how great we really are. Thank you.
All right, thanks, Carolyn. Certainly a lot of the comments and feedback that we got from that picture about how looking at this picture really puts things in perspective, and I think you really nicely encapsulated that. So we have a question here from Twitter at Q8FailAK. The rings are obviously a big feature in that new mosaic that we put out, and this person wants to know, what is the thickness of the rings?
Oh, well, it depends which rings you're talking about, but I presume he means the main rings, and they are really very thin. They are no bigger, they're about 30 feet thick, and that makes them no bigger than about 2 stories in a modern-day building. So they're very thin, despite the fact that Saturn's rings are across, they're about 1 light second. They're about 280,000, this is only the main rings, about 280,000 kilometers across. And in fact, I'd love to add this statistic because I think it's marvelous. If you took all the mass in Saturn's rings and recomposed it into a moon of the proper density for the Saturn system, it would be no bigger than Enceladus, which is a moon that's no bigger across than Great Britain. So it's tremendous visual spectacle for very little mass.
Okay. Well, we have another question from Callie Centergren on Google+. If you were planning the next mission to Saturn, what would your Cassini 2.0 look like? What instruments would it have? So maybe you can tell us a little bit about the cameras that Cassini has right now, and then, you know, if you had your wishes, what kind of camera would you really like out there?
Well, I won't so much on well, okay, like the cameras. Let me describe the Cassini cameras. They're the most sophisticated cameras. In fact, Cassini's payload is the most sophisticated payload that was ever taken into the outer solar system. And our cameras, we have 2 of them. We call them cameras. They're actually telescopes. And outfitted with many spectral filters. That's why Kunio can look at the hexagon in all sorts of different spectral filters, and they kind of slice the Saturn atmosphere and give us a shot at different levels in the atmosphere. Other images, like the one our mosaic is made of, this particular mosaic, whereas our red, green, and blue, we can use those to make what you might call natural color, but they also have scientific purposes. You look at surfaces of moons, for example, in different colors, you might be able to pick out different types of ices and so on. So, and then there's many other capabilities in the cameras I don't have the time to go into. But I will tell you, first you need to know, if you ask this this question of any planetary scientist, you'd get a different answer probably from each one. But my favorite thing to do with a mission that goes back to Saturn is concentrate on Enceladus, because we need to know, did biological processes ever get started on Enceladus? And so if we equipped a spacecraft returning to Saturn with an instrument that could scoop up materials and do a more sophisticated job of chemical analysis than Cassini is equipped to do, we might actually be able to answer the question whether or not biotic processes have gotten started on Enceladus. And then my other favorite, I would combine these into one mission, my other favorite would be to study Titan, because Titan is the only place in our solar system where we have liquid organics ponded on the surface. And it has a thick atmosphere, and in many regards, it is very similar to our planet, except that it has liquid organics. So we could study organics in situ, if you please, in a way that we can't do it any longer on the Earth, because the Earth has oxygen, and free oxygen oxidizes and destroys organic materials. So that's what I do with a mission after Cassini, and I think we should start it in 2018.
Well, that's a very passionate answer. One question that we got, I'm going to throw it back to Kunio for a minute because we had a question come in about the hexagon. This is on Twitter from JP Major. Is there, or why isn't there, a similar hexagon around Saturn's south pole?
So the meandering property of these jets, so I said that the hexagon around north pole of Saturn is a meandering jet. So the meandering property really depends on the details of the jet. So the jet around North Pole has the right speed and width to have to fit in a wave, basically to fold into six-sided shape. Saturn's South Pole actually doesn't have a similar jet stream that's wrapping around the North Pole. Well, there's a jet, but the property is actually very different from the around North Pole. There's a jet that does meander. It sometimes takes 12-sided shape. It's not very stable, but it does develop a many-sided pattern. But it doesn't look as visually striking. But it's a very similar dynamics that's happening around South Pole as well. And then, of course, we have a lot of vortices. But what we do have around Saturn's South Pole is a hurricane-like structure that we do have in North Pole. So there are similarities and differences.
Also, I mean, it is a very special sort of a thing because it doesn't even appear at the other giant planets in our solar system, does it?
No, it does not. So all giant planets, actually most planets in general, have a strong vortex around each of their poles. Venus's poles have vortices. Earth poles have jet streams, or jet streams that's wrapping around the pole is basically a vortex. Jupiter, we've actually never seen Jupiter in reflected sunlight. Jupiter's polar regions of Jupiter in reflected sunlight. So that's actually another exploration. That's going to happen soon with NASA's Juno spacecraft that will have the first view, first detailed views of the polar regions of Saturn. I mean of Jupiter, and then Uranus and Neptune. Right, we do not have polygonal structures, but they too have vortices. So yeah, right. The question was about why no hexagon or polygon around other planets. Right, we don't have polygons, but all of them do have jet streams flowing around.
Great, thanks, Kunio. We're gonna make a transition here, and I'm gonna introduce Linda next. She's going to talk about some of the mysteries that we still have to solve around Saturn, and then after that, Earl will talk about how we're going to do that. Linda?
Well, I think if someone asked me what is your favorite image, I'd have to say that the Saturn mosaic that just came back is one of my new very favorite images. It's so beautiful, it's almost heart-stopping to look at it. And with that in mind, let me go to the first slide. Let's look at that image in a very different way. And what you see when it comes up is this is a collage that includes 1,600 images that were sent by members of the public to us as part of Cassini's Wave at Saturn campaign. We asked people to go out in that 20-minute window when we were taking pictures of the Earth to raise their hand and wave at Saturn, take a picture of themselves, a selfie, and send it to us. So those pictures are here. In fact, my husband Tom and I also have our picture in there, and it's kind of fun to try and hunt down and look for your friends and family in this giant collage. And I'd just like to say a big thank you to everyone who participated in the Wave at Saturn, Smile at Saturn campaigns. You really helped us celebrate this very phenomenal event. And with that, I'd like to move on to some of the mysteries that we might solve as we continue over the next few years with Cassini. And if we go to the next image, clearly the seasons are changing at Saturn. This is a wide-angle view of Saturn with Titan crossing in front of it. Basically, you can see sort of a bluish tint or hue. If you go back 10 years to when Cassini first arrived at Saturn, the northern hemisphere was in winter and it had a bluish tint. And now we see that that tint is slowly lightening in the northern hemisphere and is moving to the southern hemisphere. The colors are reversing as we're approaching winter in the southern hemisphere of Saturn. In fact, this is a unique opportunity to look at Saturn, and we're so close to solstice, just a few years away from that summer solstice. And no spacecraft has been this close to Saturn anywhere near the summer solstice, so it offers a unique opportunity to study Saturn and Titan and the moons in this new season. In fact, if you think about it, it takes Saturn 30 years to go around the Sun a single time. So 3 decades will pass before we have the opportunity to once again observe Saturn and Titan at the summer solstice. And moving on to my next graphic, in fact, for Titan, the next few years will be some of the most exciting time for Titan weather. This image, Titan is huge. It's about the size of the planet Mercury. It has a thick nitrogen atmosphere, and as Carolyn mentioned, it's one of the only worlds besides the Earth where liquids pool on the surface. And at minus 290 degrees Fahrenheit, those liquids are methane and ethane, and there are lots of organics on the surface of Titan. If you look at this image here, this is a near-infrared image, basically a false color image. It turns out that if you look in the visible, you can't see through to Titan's surface. But if you look in the near-infrared, you can then start to see those details. And those black splotches up toward the top of the image are these lakes that we see on Titan. And it's just very intriguing to think about. Not only is Titan a giant laboratory for how life might have started on the Earth, one also wonders, could there possibly be some kind of methane-based life that might be in the lakes? And then, of course, Titan has a liquid ocean, and so perhaps in that liquid ocean, similar to what we have with Europa, perhaps that's another habitat for life as well. And so let's look at one of those seas up close. If we go on to the next graphic, this is Ligeia Mare. It's the second largest sea on Titan. It's about the size of one of the Great Lakes that you see at the U.S.-Canadian border. This lake is filled with organics, with methane and ethane, and all of the lakes on Titan seem to be congregated pretty much at the North Pole, with the exception of just a few lakes. And this is a view at radar wavelengths. So again, we can see in the near-infrared and at radar wavelengths. So we use all of the tools that we have on Cassini, including the cameras, to help us reveal Titan and its surface. And over the next few years, one of the mysteries, we wonder what will happen with the lakes. Will the methane and ethane start to evaporate? Will we see clouds of methane come over and fill what look like dry ancient lake beds at the North Pole? Will there be winds that will be strong enough to create waves on the lakes that would be able to see with the radar data? And maybe even tiny hurricanes, depending on how strong the winds blow at the North Pole. So the seasons are changing, and we're really anxious to see what will happen when that sun shines down on the North Pole of Titan. And perhaps we'll answer some of the mysteries about the lakes, why they're just so predominant at the North Pole, and how they might evolve with the seasons. Moving on to Enceladus, that's my next slide. Enceladus is one of the most intriguing objects in the solar system. It has a water ice surface, and as Carolyn pointed out, you have jets of material coming out from the South Pole, primarily liquid water. A lot of it falls back to the surface, but we also have carbon dioxide, we have organics, we have nitrogen. We basically have the ingredients there for life, possibly in that liquid water reservoir beneath Titan's South Pole. And in fact, the South Pole of Titan, or South Pole of Enceladus, is now dark. And that's very interesting because with it dark, we can now measure the heat coming out of the South Pole very accurately. And that might help tell us what's happening with Enceladus and why it is so very active. And now if we just zoom in on some of those jets up close, We have 3 flybys coming up in the end of 2015. One of those flybys is going to fly right through those jets. And it's going to be for the very first time at the time of maximum emission of those jets. The jets vary by about a factor of 3 in emission, and here for the first time, the end of 2015, we'll be able to really make measurements, more detailed compositional measurements, to find out what's coming out of these jets. And also, we'll get a chance in one of these flybys to look at the North Pole of Enceladus at very high resolution. Now with the sun high in the sky, we'll look for evidence of what might look like ancient fractures, ancient tiger stripes. And to answer the question, was Enceladus's North Pole active as perhaps the South Pole is today? So a lot of very interesting things coming up in the future years with Cassini and mysteries to solve. And finally, this set of orbits, besides returning really great science and looking at a new season on Saturn, is going to put us in great position for Cassini's endgame. These orbits are carefully positioning us so that we can get the best data possible back. And it turns out on one of those final orbits, we'll actually dive in between the innermost ring and the top of the atmosphere on Saturn and make measurements for the first time of the mass of the rings, something we really don't have a good handle on. Measure a new place in the system that we've never seen before. And that'll be very, very exciting. Also make really good measurements of the gravity field and the magnetic field around Saturn, and maybe get a handle on what that rotation rate might be for the planet. And I'll be very excited to watch when that data comes back from the very first orbit, what new discoveries might be in store for Cassini as we go into this new region that we've never probed before. And so after that, I'd like to turn this over to Earl Maize, and he'll talk about how do we shape the orbits to get the science back that'll be coming back, and what do we have for the end game. So Earl?
All right. Thanks, Linda. Maybe we could cue the first animation. This is in typical Cassini scale. This is our hour and a half of terror. Mars had their 7 minutes. We have an hour and a half. This is us passing through the ring plane and actually going into orbit around Saturn. If this had not accomplished just perfectly, we would not be talking about the mission today. This Cassini spacecraft, this was 9.5 years ago, is performing absolutely flawlessly. We are in great shape. We are 6 weeks into our 17th year in flight. As Carolyn mentioned, it took us 7 years to get here. We're 9.5 years into our mission, and everything's working well. As I said, the engineering systems are working very, very well, and the instruments are continuing to return phenomenal science. With a mission like this, at this level of duration, one of the things the flight teams have to be very careful about is consumables. The prime mission for Cassini was 7 years cruise, 4 years in prime mission, and so when you think about us now being into our 17th year, a lot of things are being used up. We have to keep very careful track of things like power and on-off cycles. Instruments are used up. We don't want them to be overused. One of the things we watch most carefully is obviously, as you can see here, is propellant. Very, very carefully watching the propellant. Cassini has 2 separate propulsion systems. A bipropellant system that powers the main engine, as the graphic shows, and we've used about 90% of that during the prime mission, and we used another 6% of that during the extended mission in the first 2 years of the Solstice mission. So right now, we've got about 4% of our propellant left. There's a Jackson Browne song about that, and running on empty is not a good situation to be in. Fortunately, we've got another propellant system. The spacecraft is also equipped with a hydrazine system that powers the smaller thrusters. They're used for attitude control and for very small vernier burns to control our trajectory. The good news is that we've got over 30% of that propellant still left, and that is more than enough to finish up the mission. The way we accomplish this, and maybe we could cue the next video, the way we do this is with a very carefully designed mission that uses Saturn's largest moon, Titan, in order to bend and reshape the trajectory. I should point out, as you'll see in this graphic, no one has ever done anything like this before, nothing this complex. What we do is by carefully controlling how we fly by Titan, we can bend the trajectory up, bend it down. Right now you can see it's in a very highly inclined orbit. We can bend it up, bend it down, we can rotate it around, we can lengthen it, we can shorten it. By carefully flying by Titan, we can add or subtract nearly 800 meters per second to the spacecraft's trajectory and pretty much go wherever we want. As you can see, we've been spending a lot of time traveling around in various parts of the Saturn system. If we've done it very, very carefully, we can actually control the trajectory to the point where we need very, very little propellant. As a matter of fact, we need hardly any. And that's why this hydrazine system works so well. What it does require, though, is very meticulous attention from the flight team. They've got to be, I like to say this is a very sporty course. Because we have so little propellant left, we've got to be very, very careful and very diligent about managing the trajectory. Even a slight miss at one of these Titans can put us off into a different path where we really don't have enough propellant to get us back on and force us into a pretty serious redesign, which we really would be ill-equipped to do at this point. So we're very careful about it. The flight team has done an excellent job of maintaining the trajectory. We do very tiny maneuvers, sometimes on the order of maybe a few tens of millimeters per second, in order to very carefully tweak the trajectory to manage its flybys and to accomplish the science for the next 4 years. So we actually have what we would call margin for the next few years. You can see, maybe I'll just point to a few things here in the animation. We have highly inclined orbits, these purple orbits, and then we come flattening back down. Now we're coming back up, as you see in the animation, flattening it back down. We will lower this back down for the final, as Linda pointed out, the final set of orbits for Enceladus, and then after that we'll wind it back up, and we're going to do something entirely differently, and that's what you can see now. The final year of the mission will be very, very different. We're going to use the final Titan flight, one of the last final flybys, Titan flybys, excuse me, to move ourselves into the very edge of the most sensible set of the rings. It's called the F ring. We're going to spend 20 orbits flirting with the F ring, and then with one more Titan flyby, we're going to, if you'll permit me a Southern California surfing metaphor, we're going to shoot the pier. There is a 1,200-mile gap between the D ring, the innermost Saturn ring, and Saturn's atmosphere, and we've done a lot of analysis on that area, and it looks to be very safe. Not very safe, but safe enough for us to go through. So what we're going to do is we're going to use the one last Titan flyby to push us into that gap, and we're going to spend 22 orbits in 22 weeks going through that period. That space. Oh, and here's a spacecraft view of this gap. As you can see, we've whizzed through very, very quickly. We'll be traveling about 30 kilometers per second as we go through there. We're going to do that 22 times. Exploring regions that we have never seen before, in sampling Saturn's atmosphere, the inner rings of the dust, and getting gravity measurements that we've never been able to accomplish. And then, finally, on September 11th, 2017, we're going to use one last Titan flyby to nudge us into Saturn's atmosphere. The flyby is going to be such that we will, be irreversibly entering into Saturn's atmosphere, and at 30 kilometers per second, the spacecraft will be destroyed almost immediately, nearly 4 days after the flyby. Thus, the end to an incredibly glorious exploration of the Saturnian system, a legacy of science and science data and engineering achievements that will, I don't believe, be duplicated for a very long time, and I think a wealth of information for generations to come.
Yes, our final goodbye to Cassini in September 2017.
Thanks, Linda and Earl. I love that picture of Cassini kind of being crushed by the embrace of Saturn, whom it's been circling for so long. Well, sounds like Cassini really has a great to-do list in front of it. I have a question, this one I think Linda can take, on Twitter from Tim Johnson, who is asking on behalf of the Connaught School. Damien from this school asks, what kinds of storms are common on Saturn?
The kinds of storms that are common on Saturn, we've had one very huge storm. It started in December 2010 and lasted for about 9 months. So we can have huge storms that happen about once every 30 years around Saturn. We can have giant hurricanes at the north and south poles of Saturn, and can also have smaller vortices. There's a region we call Dragon Alley, early in the mission in the south, where we had lots of storms and lightning with it.
thing I remember you're telling me is that these huge storms actually occur once every 30 years, or they had been in the past, but did we get it early? Will we get another one?
Yeah, it turns out that these storms about once every 30 years tend to occur closer to Saturn's solstice. And so we got this storm a little bit early, sort of in Saturn's spring. And so we wonder, perhaps, is there another giant storm in store, or just like Earth weather is variable, did we get our big storm early?
Great. Okay, well, we've got another question. This one I think I'm going to maybe send to Carolyn. It's Reginald on our Ustream box is asking, are the cameras capable of gathering spectra to identify chemical bond types in the clouds at Saturn?
Cameras generally don't, unless they're outfitted with a spectrometer. And for example, the VIMS instrument has an imaging component and then also has a spectrometer with it also in both the visual and in the infrared. Unless you have an instrument that can spread the light out very finely in wavelength so that you have high resolution in the wavelength domain, you generally can't do a whole lot of detailed chemical identification. So we don't have that with the Cassini cameras. We have very broadband filters and then moderately broadband. So we're not so much in the business of identifying whether or not it's, you know, well, I can't even guess right now, but we're not identifying particular chemicals or chemical bonds. What we can do is we can say that we have an ice on the surface that absorbs a lot in the infrared, but maybe not so much in the ultraviolet. In some sense, colors is really the spectral information that we can get with the cameras.
You mentioned that Cassini actually does have other capabilities to do something like that.
Are you asking me?
I'm going to throw it back to Linda just to mention it for a second. I think you might be on mute, but does Cassini have something else that could do science of that type?
Right. For composition, we have an instrument called the Composite Infrared Spectrometer. It looks in the mid and far IR, and it can actually make measurements that tell you what kind of molecules that you have in the atmosphere. Not only hydrogen, which is the main constituent of Saturn's atmosphere, but you can also measure things like methane and hydrocarbons. It can measure those bonds, I think, that we're being asked about. So we have that with the Composite Infrared Spectrometer. Then the Visual and Infrared Spectrometer also can make measurements of the composition.
Thanks for answering those questions, Linda and Carolyn. So I've got another hexagon question for Kunio, and maybe you can also elaborate some more on the storm, since I think you actually did your dissertation on storms on Saturn. So here's a question from Veronica Vixen on Twitter. Is the hexagon on the actual surface of Saturn, or is it an optical illusion, or gases like the clouds?
Okay, it's definitely not an illusion of any kind. This is a real feature that does exist, and it has been there since 1981. It is gas, so it's clear. Well, it's a pattern of clouds, so it's gaseous. It's not a solid feature that we have on the surface of Saturn. Saturn is a gas giant planet, so there's no such thing as mountains and valleys or even oceans on Saturn. All we have is a bottomless atmosphere. If you try to land on Saturn, we're just going to sink to the core, basically, of the atmosphere. There's no solid ground we can stand on. But the hexagon is a real feature. It is a jet stream, as I said earlier. It is folded into six-sided shape, and it is a very stable feature. That is a surprising part of it, and we are studying that feature. And you said there was a question about the storm as well? Or should I just launch into the discussion?
Well, why don't you just tell us a little bit more about the storm? We were talking about how you know, they seem to appear once every 30 years or so. I mean, was the storm that we saw, for instance, a couple of years ago the biggest that we've ever seen, comparable, or give us a little perspective?
Right, the 30-year storms. Yeah, so this is a very special kind of storms because Saturn is, of course, spherical. but what's special about these storms is that it lasts so long and it's so big that it actually wraps around the planet. It's a single thunderstorm that blows up in one spot, but the cloud extends out so much. Saturn's a big planet to start with. On that big planet, this storm cloud completely wraps around the planet. So this is a very special kind of storm that actually wrap around the planet. Yay, there's the image. So this is, I think this is images from around February or March of 2011. And this is, you're seeing the phase of the storm that in which the storm has not wrapped around the planet yet. At the left end, this sort of looks like a comet. So the active thunderstorm, the most intense thunderstorm, is happening at the left tip of this image. That's where the storm's core is located. And then that storm cloud is getting blown downwind by other jet streams that's surrounding the region. And so this is about 3 months into the storm. So the storm started in December of 2010. So I'm guessing, just I've seen these pictures hundreds of times. So it looks like a morphology we had in like February, March of 2011. At that phase, the storm had wrapped around the planet only half of the longitude. So it has gone around only half of the planet. But in June of 2011, the storm's head actually caught up with the tail of the storm. And then when the head bit the tail, somehow the head disappeared. So that was a really exciting event that we were not expecting it to happen that way. The storm lasted for 200 days, 200 Earth days, and then when the head caught up with the tail, the head actually disintegrated, and that's how the storm ended. So that was a really dramatic event.
Can I add something?
I like your reenactment. Oh, sure. Okay, Carolyn?
I just want to say about this storm, another really important aspect of it is that they're estimating from the lightning strikes that occur in it. The estimate of the total amount of energy in this storm makes it comparable to the amount of energy that's coming out of Saturn. So that means that this storm and the frequency of the storms once every 30 years and so on, these storms are playing a role in the thermal evolution of the planet. So that was, to me, as a non-atmospheric scientist, that was one of the most exciting discoveries in being there to witness this event that happens only once every 30 years, and it's just another example of why it is so important, if you really want to understand how planets work, we need to have our robots, our machinery, in orbit around planets, having the time to monitor them in order to understand them in full.
Thanks, Carolyn. So we're getting a lot of great questions on our social media outlets, and in fact, we're getting some budget questions, like from Crystal on Google Plus about given the announcement of restructuring of NASA's planetary sciences, what's the future of Cassini? I think that these are all great questions, and we don't yet know the answers. We have a lot yet to learn at Saturn, and we hope the mission continues through 2017. But you can always ask your questions to NASA headquarters. They're the folks that make the decisions about the budget. So we're going to do one last question, and this one I'm going to throw to Earl. We have a question from @TheRealJav on Twitter, and so he's asked, how many more years of operation do we expect to get from the Cassini probe? So I know that we've got this kind of planned dive into Saturn in 2017, but have we basically eked out the last fumes here on Cassini, or could it go for longer?
We could maybe go a little bit longer, but not much. One of the very important things about end of mission scenarios with these probes that are exploring systems that have potentially prebiotic environments like Enceladus, Titan, or in the case of Europa at Jupiter, is that we must dispose of the spacecraft cleanly. And so we can't just let it run out of propellant and drift aimlessly in the system. We have to have enough margin left in the system to dispose of it properly, and that is into Saturn's atmosphere where it can't possibly contaminate anything. So we could maybe eke out a little bit more, but we've got it planned now to the point where it's a perfect end to the mission. We'll have very little propellant left, and that's, I think, the best way for us to proceed.
Great. Well, we've had a really wonderful Google Hangout. Thank you to everybody who's participated. You know, the conversation doesn't have to stop here. We can continue to work on all the questions that we can get to on social media. Cassini has a Twitter account at Cassini Saturn. We also have the web pages, and we've got a slate sort of showing you how you can keep in contact with us. Kunio has also volunteered to answer some more questions on his Twitter account, and that's at Windy Planets. So thank you very much to everybody who participated in our show and asked us questions, and we hope you guys will